Hello everyone. So today we are going to start uh, solving the problems on double pipe heat exchanger. So before we go to the problems, first we need to understand that the heat exchangers, the problems may be of two types. The one is the analysis type, and another is the design type. And then each problem they have there are two methods of solving them. The one is the LMTD method and another is this ENTU method. So whether you have an analysis type of problem, that means that you have given the heat exchanger design and you need to find out the unknown parameters. That may be temperature, that may be a heat flux, that may be heat transfer coefficient, etc., etc. And in the design type of problems, that the heat exchanger is not given, only the requirement is given, and then you have to select the heat exchanger of from the catalog, and that can meet the your requirement. Again, when you do the design analysis, then you will have two methods. So either one you can choose, either LMTD method or ENTU method. ENTU means effectiveness, NTU, that is number of transfer unit methods. So if you see the this example, example 8.4, and so this example is based on the LMTD method, and it's an analysis type of problem. That means the heat exchanger design is given in this problem. So the water at a temperature of 79.45 degrees Celsius and a mass flow rate of 0.63 kg per second is used to heat ethylene glycol. The ethylene glycol is available at 32 degrees Celsius. So ethylene glycol is your cold fluid and the water is your warm fluid, and this is the initial temperature for the water and this is initial temperature for ethylene glycol with a mass flow rate of 3.78 kg per second. A double pipe heat exchanger consisting of 1 1/4 standard type M copper tubing inside of two standard type M copper tubing. So there are two tubes. The outer tube is two standard, the inner tube is 1 1/4 standard, and both are type M copper tubing. The exchanger consists of two double hairpin double hairpin exchangers, and each of length 8.83 meter. The flow configuration is such that both fluids travels in series throughout. So the both fluids travels in series. In series means that the 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 heat exchangers, the two double hairpin heat exchangers, they are connected in series. Determine the outlet temperature of both fluids using the counterflow and again using the parallel flow. So the two double hairpin heat exchangers. So let's say like this is one hairpin and this is another hairpin, and when you connect them in series combination, so you can see that it will look like this. So this is the one hairpin, as we can see, and this is another hairpin, and when you combine them, so it will look like this, the series combination of the two hairpin. And the length, this length from this point to this point, this length is given as 1.84. So the total length of the heat exchanger where the fluid is traveling from here to here and all the way here, so the length is multiplied by 4. So 1.83 multiplied by 4 becomes 7.315 meter total length of the heat exchanger. Okay. Now for the properties of the heat exchanger, so there is an important point here, that what are the assumptions that we are taking while solving this problem, that we are assuming the steady state conditions. So steady state conditions, and then the fluid property should be evaluated at mean temperature. But here in this problem we see we do not have the final temperature. The water is given, this is initial temperature, and this ethylene glycol, this is initial temperature. So the final temperatures we don't have. So as a first attempt for the properties, what we do, we take the average of these two temperatures. the inlet of the water and inlet of ethylene, and we take the average of these two, and then we will calculate, we will find the properties from the table at this temperature. So this temperature uh, which is which come out to be which come out to be 55.8 uh, 55.83 degrees Celsius. So the properties will be calculated at this temperature initially, but remember that the later on we will repeat the procedure and the properties will be calculated at the average temperature when we know the final temperature of water and final temperature of ethylene glycol. Okay, so these properties are evaluated at the mean of the inlet temperature. So that is 55.8 degrees Celsius for water and for ethylene. So both are at the same temperature in the beginning, and these properties can be seen from the table. Now what else is given, that the tube diameter is given, that the outer tube is 2 standard, inner tube is 1¼ standard, and type M copper tubing. So we can see the size for the pipe, what is the inner diameter of the pipe, what is the outer diameter of the pipe, and what is the inner diameter of the second pipe, that we call it annulus. Second pipe, outer pipe, we will call it annulus. So all the three diameters are given, and then we can calculate the flow area. What is the flow area inside this pipe? So this is the pipe flow area for the pipe, and this is the flow area for the annulus. So we need to calculate this, so we can calculate this. So remember that in this book, the good thing is that they have mentioned the procedure step by step, like your step A, your step B, your step 3, step C, and step D. So you follow the step by step procedure, right? So we calculated the flow area, and then we need to calculate the flow velocity depending upon the mass flow rate. So the mass flow rate is given for both. The mass flow rate for water is given here, and the mass flow rate for ethylene is given here, and we know the density of both, and we know the cross section area for both, so we can find out the velocity. So the velocity of the flow in pipe and the velocity of the flow in annulus. In the next step, we will calculate the hydraulic diameter and equivalent diameter. So remember, as for the pipe is concerned, the inner diameter of the pipe is your hydraulic diameter, and the inner pipe you don't need to calculate the equivalent diameter, because equivalent diameter and hydraulic diameter is same for the inner pipe. As for the outer pipe is concerned here, for the outer pipe we need to calculate the hydraulic diameter and we need to calculate the equivalent diameter. So we use the formula as we discussed in previous lectures, that the hydraulic diameter, and this is the formula for equivalent diameter. So once you have the hydraulic diameter and equivalent diameter, we can calculate the Reynolds number for the pipe, flow in pipe, and the Reynolds number for the flow in annulus. Remember that while we calculating the Reynolds number for the annulus side, we are taking it equivalent diameter, not the DH, because the DH we will take for pressure drop calculation, and D we take for heat transfer calculation. So here we are taking the DE. So that means this Reynolds number will be taken for heat transfer coefficient. So now we have the Reynolds number for pipe flow, and we have the Reynolds number for annulus flow. And now we will use the correlations to find out the Nusselt number for the pipe flow and for the annulus flow. So in both cases here we saw that the Reynolds number, the value of the Reynolds number is more than 10,000. So which means that both cases the flow is turbulent. So we use the turbulent flow correlation in this case. So the turbulent flow correlation, right? So but remember that in the fluid, the exponent of Prandtl number, this is change, because the water is warm fluid and the ethylene is cold fluid. So depending upon the warm fluid and cold fluid, the index for the Prandtl number is change. Here it is 0.3, here it is 0.4. So we calculate the Nusselt number for both, and with the help of the Nusselt number, using the formula of using the relationship between the Nusselt number and heat transfer coefficient, we can find that what is the heat transfer coefficient. So the heat transfer coefficient we can find HI, and then we will put this relationship. The heat transfer coefficient for the pipe is equal to the heat transfer coefficient HI inside multiplied by IDP divided by ODP. So we use this expression to find out the HP. So first you find out HI and then substitute the HI here and then you find out HP. So the pipe side heat transfer coefficient comes out to be 3366 watt per meter square Kelvin. And then for annulus side heat transfer coefficient. So the annulus side heat transfer coefficient using the formula come out to be 2357 watt per meter square Kelvin. Now we need to calculate the overall heat transfer coefficient. So the overall heat transfer coefficient, which is represented by U naught. So the 1 over U naught is equals to 1 over HP plus 1 over HA. So when you substitute the value of HP and HA, so the overall heat transfer coefficient comes out to be 1386 watt per meter square Kelvin. And we are using the log mean temperature difference method. So we will use the expressions of the log mean temperature difference method. So for the log mean temperature difference method, or we call it LMTD method. So for the LMTD method, depending upon the parallel flow or counter flow, we need to calculate the parameter E. So the parameter E for counter flow, which is this, so we need to calculate this. And what we need to calculate this? We need to calculate overall heat transfer coefficient, area subjected to heat transfer, and R minus 1, and this MC CPC. So R is the ratio of the capacity, that is CPC for the cold fluid and divided by the warm fluid 3.65. So we calculate the R, which come out to be 3.65, and then we calculate the area subjected to heat transfer. So the area subjected to the heat transfer is the outer wall area of the pipe, inner pipe, outer wall area of the inner pipe. So outer wall area of the inner pipe along the length of the heat exchanger is pi ODP multiplied by L, which is come out to be 0.803 meter square. Then we substitute this R and A naught values into this E expression, which is for counterflow, is come out to be 1.358. Then we use the expressions for the exit temperatures, so final temperatures T2 and T2. And remember that as we discussed in our previous lecture, that capital T2 indicating the warm fluid and small t2 indicating the cold fluid. So we calculate the warm fluid exit temperature, which come out to be this value, and the cold fluid, which is ethylene glycol in this case, outlet temperature will come out to be 36.5 degrees Celsius. So now we got the final temperatures for the fluid. So this is the analysis of the heat exchanger with the help of the correlations for Nusselt number. So if we consider the parallel flow, then we calculate this parameter for parallel flow, and we use this parameter to calculate the final temperatures, which are 64.1 and 36.45 degree Celsius. So we got the final temperature now here, and after that what we will do, we need to check and we need to calculate the properties at the average temperature to make sure that the properties does not differ much. So we calculate the average temperature of the warm fluid. So this is the average temperature of the warm fluid, and then this is the average temperature for the cold fluid, and then we repeat the procedure taking the properties at this temperature and at this temperature. Then we go back to our first step where we started. We started from here. We taking the properties, right? So here we are taking the water properties 55.8 and ethylene glycol properties again the same 55.8 degree Celsius. But now for the second trial, for the second time, we need to take the properties for water at 71.6 degree Celsius and for ethylene glycol 34.35 degree Celsius, and then we have to find out again what are our final temperatures, right? So So we have to do the second iteration if to check that our final temperature and properties are not very much different. So the system is now reanalyzed using the properties evaluated at this temperature, and if necessary, a third iteration should be made that a better estimate of the outer temperature is obtained. So that is only if necessary. Like after the second iteration, if your properties differing too much, then you do the third iteration, and if not differing too much, then you don't need to do third iteration. Like in this case, it is 71.6 and it is 72.2. So the average temperature after the first trial it was this, and after the second it is this. So it is almost same, so no need to do the third iteration. The same here, this is 34.35 and this is 34.3, so no need to do any further iteration. Okay, so we got this as our average temperature. Okay, so if you summarize the information that you got, that the overall heat transfer coefficient we got is this, and the if we consider the final, if we consider the counter flow, then the outlet temperatures are these, and if we consider the parallel flow, then the outlet temperatures are these. So which clearly shows that the warmer fluid is the temperature for the parallel case is more. That means the warmer fluid is losing less heat, and for the parallel case, and the cold fluid is not the cold fluid temperature is almost same, so it is not much difference. Okay, so and then the next step is that you have to make the heat balance, whether the temperatures you obtained is correct or not. So you check the heat balance for the warm fluid. So this is the heat balance for the warm fluid, and this is the heat balance for the cold fluid, and this is the heat balance with the help of log mean temperature difference and overall heat transfer coefficient. So this heat balance also you have to do, and you have to check that all the three heat comes out to be same, because basically there is no loss and there is no work done, so the heat exchange between the two fluids should come out to be the same. The heat gain by the cold fluid should be equal to the heat loss by the warm fluid. Okay, so here we complete the analysis part, and then there is another thing that we need to add into our solution is that is your Fouling factors. So if we take into account the Fouling factors in our design, then we need to find out that what is the Fouling resistance for the two liquids that we have. So we have the distilled water, we have the water, so we can take the Fouling factor for the water, and we have the ethylene glycol, which is an organic liquid, so we can take the Fouling factor resistance or Fouling resistance for the ethylene glycol. So this is additional resistance in addition to your convective resistance inside the fluid and your convective resistance on the annulus part. Right. So the overall heat transfer coefficient after taking into account these two resistances will be calculated like this. So this is what you calculated before, 1 over u naught. So this is the same value you calculated before. So 1 over u naught plus the Fouling resistance for the fluid inside, and this is the Fouling resistance for the fluid outside, and then you are calculating the overall heat transfer coefficient u. So now the u come out to be 908, and before the u was 1260, and now it is coming out to be 908. So when you take into account the Fouling resistances, then the overall heat transfer coefficient is reduced. So with the help of this overall heat transfer coefficient, if you calculate the final temperatures again for counterflow case, then the final temperatures will be changed. So when do we take the Fouling resistance into account? The Fouling resistance should be taken into account when your heat exchanger is 1 year or more old. If your heat exchanger is old more than 1 year, then you need to take into account the Fouling factor or Fouling resistances. And then this is the temperature after you take into account your Fouling resistance, and this is for counterflow. And then you again make the heat balance, and then you see that now it come out to be 29.1 kilowatt, and before it was 38.17 kilowatt. So that means that the heat exchange between the two liquids is reduced when you take into account the falling resistance, falling factor or falling resistance. Now, summarizing the information, that when you are not taking into account the falling resistances, that means your heat exchanger is new. And when it is new, then your heat transfer coefficient and your final temperature for the warm fluid, your final temperature for the cold fluid, and the rate of heat transfer between the two fluid. And when you take into account the falling resistance, that means that the heat exchanger will give this performance even after 1 year. So the U come out to be 908 T2, and this for cold fluid T2, and then this is rate of heat transfer. And remember that these data are for counterflow. So what comments we can make for this solution? So the result shows that there is a small difference between the parallel and counterflow performance of the heat exchanger. And the counterflow performance is usually preferred because it gives higher rate of heat transfer and higher change in the fluid temperature. What about the properties? The temperature at which the properties are evaluated had a little influence on the outlet temperatures, but this is not always. Sometimes the change of property is big with respect to the temperature, then it has a large influence, and sometimes the change in property is small, then it has a small influence. So sometimes the properties change are drastic with respect to the temperature, then your performance analysis become very much proper temperature sensitive, and then you have to take the accurate average temperature of the fluid to find out the accurate properties and accurate performance. So when the falling effects were taken into account, the overall heat transfer coefficient is reduced from 1260 to 908 watt per meter square Kelvin. And when you take the falling factors into account, your performance is reduced, and that indicate that that will be the performance after 1 year of usage. So when the heat exchanger is new, you don't need to take into account the falling coefficient or falling resistance. When the heat exchanger is old and more than 1 year old, then the falling resistance should be taken into account. So this is all about the analysis type of the problem. So the problem may be of different nature. Here what is unknown was the final temperature. Sometimes they may ask you what is the overall heat transfer coefficient, what is the number of transfer unit, and what is the rate of heat transfer, and what is the final temperature. So the similar problem can be solved using the ENTU method. So the similar problem can be solved using the ENTU method. So it is up to you that which method you want to use. You want to use LMTD method or ENTU method. So the next example is given in the book 4.5, which is based on the ENTU method. So you can see that the both methods, they are slightly different and lead to the same answer. Okay, so here we finish this tutorial. So thank you very much.